Hey everyone, and welcome to The Explainer. Today we're jumping right into a really foundational piece of modern networking. We're going to be talking about the absolute silent hero of the internet, Network Address Translation, or NAT for short. We'll break down the theory and the mechanics behind it so it all makes perfect sense. Let's get right into it.
So, have you ever wondered how many devices in your house can access the internet using only one public IP address? I mean, really think about it for a second. You've got your smartphone, a laptop, maybe a smart TV or a gaming console, and they're all connected to your home Wi-Fi at the exact same time. But your internet service provider, they only gave your house a single public identity on the web. So how is that even possible without everything just crashing into each other?
Well, the answer to that little mystery is NAT. Network Address Translation is basically this process configured on routers and firewalls that allows all those private IP addresses inside your local network to actually communicate with public networks like the internet. In the simplest terms, NAT is a translator. It modifies the IP address info in network packets right as they pass through the router. Without this absolute lifesaver of a technology, every single device in the world would need its own unique public IP address. And fun fact, we officially ran out of new IPv4 addresses way back in 2011. NAT literally stepped in, saved the day, and has been keeping the internet running ever since.
All right, so let's look at this boundary between the inside and the outside. On one side of the network, you've got your private IPs. These are addresses like 192.168.whatever or 10.whatever that your router hands out to your personal devices. These are completely hidden from the outside world. Then, on the other side, we have public IPs. These are the real, globally registered internet addresses that outside servers and websites actually see and interact with. NAT sits exactly on the border of these two worlds, acting as the ultimate border control and translator for all your data. How NAT actually works, the life of a packet. Let's follow a piece of data on its journey to see exactly what this translation looks like in practice.
Okay, let's walk through the 6 steps of a packet's life. Step 1. Your device, let's say your laptop, creates a packet of data using its private IP address and sends it out. Step 2. Your router receives that packet. Step 3, and this is where the magic happens. The router strips away your private IP and swaps it out, translating it into its own public IP address. Step 4, that packet travels out into the wild internet under its new public identity. Step 5, the website replies, sending the response back to your router's public IP. And finally, Step 6, the router translates that public address back to your laptop's original private address and delivers the data. The crazy part? Your laptop never even knows the translation happened. It's totally seamless.
Now you might be wondering, how does the router not get completely confused? How does it know which device gets the returning data? Well, it uses a NAT translation table. The router keeps this really strict active record, mapping a specific private IP, say 192.168.1.10, to its public IP, like 105.20.30.50. It actively tracks these connections, so when the data comes back, it just checks the table, finds the exact laptop that asked for it, and forwards it along perfectly.
Next up, the 3 types of NAT. Network administrators use different strategies here depending on what they need to accomplish.
The first 2 types we have are static and dynamic NAT. Static NAT is a permanent one-to-one mapping. You lock one specific private IP to one specific public IP, forever. This is absolutely crucial if you're hosting something like a web server or an email server that the outside world always needs to find at the exact same address. Dynamic NAT, on the other hand, is a bit more flexible. Instead of a permanent setup, the router holds a whole pool of public addresses. When a private device needs the internet, it just borrows an available public address from that pool temporarily and gives it back when it's done.
But wait, neither of those really solves the problem of a home network with lots of devices and only one public IP, right? To understand the third type, imagine a large office building. Employees all have internal extensions like 101, 102, and 103. They can call each other easily all day long. But when any of them calls a client on the outside, the client's caller ID only ever shows the company's main phone number. Everyone in the building shares that one main external line.
And that analogy hits the nail on the head for our third and honestly most important type, PAT, or Port Address Translation. You'll also hear this called NAT Overload. PAT is the most commonly used form of NAT in the world. It is the exact technology running on your home router right now. PAT allows dozens or even hundreds of private devices to share one single public IP address at the exact same time. And it pulls this off by using different port numbers to distinguish every single active connection.
Here's where it gets really clever. Notice how different devices, say PC1, PC2, and PC3, all have different private IPs, but they're getting translated to the exact same public IP. So how does the router tell the traffic apart? Look at the very end of those public addresses. By assigning a unique port number to every single session, like 1025, 1026, 1027, the router makes absolutely sure that PC1's Netflix stream doesn't accidentally end up on PC2's web browser.
All right, moving right along to navigating NAT terminology. If you're an IT student or studying for a certification like the CCNA, there are a few terms you absolutely need to know.
Don't let this matrix intimidate you. The crucial point here is just remembering two sets of perspectives: inside versus outside, and local versus global. Inside means our network. Outside means their network, like the destination web server. Local means how an address appears privately on the local network, and global means how it appears publicly on the internet. So your laptop's private IP, that's the inside local address. When NAT translates it to the public, it becomes the inside global address. The server you're talking to has an outside global address out there on the real internet, and if your router translates it on our end, it views it as the outside local. Just keep repeating. Inside is us, outside is them, local is private, global is public. You've got this.
Finally, let's wrap up with our pros, cons, and the IPv6 future. Like any piece of technology, NAT comes with its own set of trade-offs. The upsides here are just massive. First and foremost, NAT single-handedly conserved our incredibly limited supply of IPv4 addresses. It also provides a really fantastic inherent layer of security. Because your internal IPs are completely hidden, malicious actors on the internet can't easily initiate a direct connection to your personal laptop. Plus, it reduces costs for organizations since they only need to buy a few public IPs instead of thousands, and it gives them the flexibility to change their internal network setups without breaking their connection to the outside world.
But hey, there are disadvantages. All this translation work takes processing power, meaning routers just have to work harder. The biggest issue, though, is application compatibility. Things like VoIP phone calls, online multiplayer gaming, and peer-to-peer file sharing, those applications really prefer direct end-to-end communication. When NAT is constantly scrambling the IP and port info in the middle, users can experience hiccups, strict MAT-type errors, or even dropped connections. Also, because so many devices are hiding behind one public IP, tracing a specific action back to a specific individual device becomes much, much harder.
Which naturally brings us to the future, IPv6. You see, IPv4 required NAT because we just didn't have enough addresses for the billions of devices coming online. But IPv6 was designed with an incredibly massive address space. We are talking so large that every single grain of sand on Earth could have multiple IP addresses. Because there is such an absolute abundance of IPv6 addresses, NAT is generally unnecessary in an IPv6 network. Devices can finally have true end-to-end connectivity again without the router having to constantly play translator.
Until the whole world fully transitions over to IPv6, we are going to rely heavily on this translation process. NAT is one of the technologies that allows billions of devices to communicate on the internet every day. It truly is the silent coordinator keeping our digital lives running smoothly. Thank you for watching. If this explainer helped you understand NAT, please like this explainer, subscribe to the channel, and turn on notifications for more networking lessons. Keep learning, and I'll catch you in the next one.